Hello, I'm DJ Rao. This is the fourth part of the five-part series designed to provide a rapid introduction to concepts in C++ so that programmers can quickly ramp up on developing programs in C++. Ensure you view the other four parts of this tutorial that cover the key concepts required for developing comprehensive programs in C++. This part focuses on containers, specifically vectors, unordered maps that are often used in programs. Data structures are used to streamline data management by storing and retrieving data in memory. Since they contain data, they're also called containers. Different data structures or containers have different properties and time complexities. C++ has many containers. Look at the comprehensive list of containers on the online documentation. The two most commonly used containers are studvector, which is essentially synonymous to a conventional array, and a vector stores a list of values that are accessible using an integer index just like an array. The unordered map enables access to values based on an index that can be of any type. It can be an integer or an object. And the unordered map uses a hash value in order to access information in this data structure, so it is also called a hash map or a dictionary in other programming languages. Let's start with a vector. To work with a vector, you have to pound into the vector header, and when working with vector, you have to specify the type of information the vector has to contain in angle brackets. Here the type can be a primitive or a non-primitive data type, and in this context the type is called a generic or a template parameter. Of course, here you're working with list of individual values, so each element has to be independently operated on to read or write information, which is very similar to array processing. Let's look at a few examples. Here is a vector of 6 integers. Notice how the integer int is in angle brackets to tell the vector that it's going to contain integers. And with a definition like this, you should be able to visualize this data structure as an array of 6 tens, because 10 is the initial value that's been specified. And there's a logical index position associated with each one of these entries. And note that index positions for a vector start with 0. Now let's look at another example where we have a vector of strings. Notice that the string is in angle brackets. And here the name of the vector is words, and it's initialized to 3 strings. Notice how the initialization is done by putting the values, comma separated list in curly brackets. Again, you should be able to visualize this vector where the values are 1, 2, and 6, and they are logically in index position 0, 1, and 2. And notice that you can use access information in a vector as if it's an array. So when you use the notation words within square bracket 1, words of 1 refers to the string 2 in this vector. Vector has a few common methods that you have to know. There is a pushback method that is used to add elements, and this pushback method adds elements to the end of the vector. If you want to insert elements at some index position I, then you use the insert method, and notice that the idiomatic use of how the insert method works. Here, the insert method uses what is known as an iterator to identify the position where a value has to be inserted. So here, the method begin returns what is known as an iterator to the beginning of the vector, and from there we add I or offset I positions in the vector to insert the value test. Similarly, to remove an element at index position I, use the erase method, and again use an iterator notation where we say from the beginning of the vector go to the ith position and erase an element. Iterators are important concepts and are used in almost all major programming languages. Iterator essentially gives you an abstract or a data structure agnostic API for accessing data. Here, vector typically you can use an integer, but think of other data structures like maps or sets where an integer index position doesn't make sense. However, an iterator does make sense and it'll be able to adapt to different data structures. So it's a good idea to start working with iterators and using the iterator notations so that you start getting a little bit more comfortable working with iterators as we go through this series of presentations. When working with different kinds of data structures, it is a good idea to start thinking about aliases for data types. C++ permits aliases to be associated with different data types. Aliases can be used to shorten names of data types so you don't have to type long names for these different data types that we are going to be using. Aliases also add more meaning to improve readability of programs. It eases changes to data types during development and maintenance so you're not locked into one type of data, and if you make small modifications, you don't have to change large parts of the program. Aliases in C++ are created via the using keyword. Here's an example. Here we are creating an alias called number to the data type int. So now, once it is defined, number is an alias to int, and now number and int can be used interchangeably. That means wherever you would use int, you can use number. And now, for example, when I'm defining the variable value, I've used the data type number, which is essentially an integer, and you can start working with these types of aliases as you develop programs. Aliases can also make programs easy to develop, understand, and maintain. So for example, look at this set of methods. They all have integers as return values. And the question is, what do these integers mean? What is the return values of these methods? You would have to actually look at the documentation in order to understand what these methods do. Instead, if we used aliases, notice here we are using aliases called error code user ID. So when you look at the check method, now you can tell that the integer being passed to it is a user ID and the return value is an error code. So it tells you something about the error status of the calling that method. Yes, error code is an integer, but now when you look at the method signature, you have a lot more semantic information associated with the return value, so you can make a more informed and a more explicit API when you develop methods and functions. This is an important advantage of creating these aliases as well. Now let's look at how to work with a std vector. Here I'm going to create an alias called strvec, which is to a string vector or a vector of strings. Now let's write a simple method which is to find the maximum value in a vector. So here we're working with strings, so finding the maximum value implies that we are looking for a word that would occur last in the English dictionary order. So I'm going to create a method called maxVal. Notice that it takes a constant reference, so that way we will not make copies of large vectors. And then it's going to return the string value, which is going to be the maximum value in the list. Next, I'm going to initialize a variable called max with the first value. Notice the use of the auto keyword. The auto keyword is very handy and you should start using it very often. The auto keyword basically tells the compiler to deduce the data type for the variable max based on the value that it's initialized to. In this specific example, vector of 0 is a string, hence max will also be set to a string. Versus if the vector was different, it had a different value in the container, this code will automatically adapt to it. So if we were to change string to an integer in the vector, this part of the program wouldn't have to change at all, and auto will take care of adapting or changing the data type of max appropriately. Of course, now we are going to iterate over that vector. Notice that again I'm using constant references so that I will make copies of strings, and I'm using constant because we are not modifying values in the vector. And then I'm using the standard max method to keep track in the maximum value, and then finally returning the maximum value from the method. Let's look at another example where we want to return strings at even indexes in a vector. So for example, if the vector has 1, 2, and 3, we just want to return 1 and 3 at even index position because 1 is at index position 0 and the word 3 is at index position 2. So I'm going to create a method called @evenPath. That's again going to take a constant vector via reference so we don't make copies, and it's constant because we are not planning to modify the input vector. And this method is going to return a vector back. So we're going to create the return vector. It's going to return by value here. So notice how it is set up. We are returning the object as a result. And then we are going to iterate over the list of values. Notice the use of the size t data type. This is unsigned long, similar to how we did with strings. If you used integer here for I, the compiler will generate a warning because vectors can contain 2 terabytes of entries, so an integer will not fit that range. And of course, here we are skipping by 2 on the iterator. That's why it's I plus equals 2 there. And then we take those entries and push it back to the return vector. Notice how source is accessed as if it's an array. And this is a correct and consistent way of accessing information in a vector. Let's look at another example of finding elements in a vector. Again, I'm going to assume it's a string vector, and I want to create a method called findVal that takes a vector to search in and a value to search for. So it is going to search for the given value in strList. So I'm going to iterate over each entry in strList, check to see if that entry is equal to the value I'm looking for. If it is, then I return true to say the value was found. Otherwise, I'm going to return false and end the for loop. That means we have iterated over each entry and we didn't find a matching value, we return false. Just a simple example to illustrate the use of the, notice the use of the auto keyword in that for loop as well. Of course, instead of writing the find val, we could have used a standard C++ algorithm called find. Notice how the find algorithm is done. You pass it the beginning of the an iterator to the beginning of the string list, iterator to the end of the string list, and the value to look for. If the value is not found, then it'll return end. However, if the value is found, it'll return an iterator to the position. So that's what that logic does by saying if find a value, and if it is not equal to the end of the vector, that means we search to the end of the vector, we don't find the value, then this method returns true or false automatically. Of course, do look up other methods in the algorithm header in the online documentation. This algorithm header has all of the key computer science algorithms that you should typically know and you would use. So all of the sorting, searching, and the partitioning algorithms are all in the algorithm header. And do look up some of these algorithms, as it'll come in handy for some of the complex software systems that you may develop. Let's look at another example of processing streams with vectors. Here's the problem that we want to work on. Given a string with comma separated values, we want to convert it to a vector of words. So I'm going to work with a vector of strings. I'm going to develop a method called split that's going to take a line that it needs to be split that needs to be split into individual words. And of course, we're going to create a vector that contains these words, and we are going to return that vector. We're going to use the standard pattern to be able to read a word until we hit the end of an input stream and push the word into that vector. Here we are going to use an input string stream to read words from the line, so it is convenient to reuse the paradigm from the previous presentations. There is one gotcha here. The input stream assumes that values are separated by white spaces and not commas. However, here I want to work with data that is separated by commas. So there is one modification that we need to do, which is to replace all of the commas with white spaces. For that, I'm going to use the replace method from the algorithm's header. So I'm saying replace from the beginning of the line to end of the line, all of the commas with blank spaces. Now that once replace is done, the commas are replaced with white spaces, and our standard paradigm of being able to read words works just fine, and this method correctly reads word by word from that string and pushes it into a vector and returns a list of words in a vector. Alright, now let's switch gears and look at unordered maps. Recollect that unordered maps are also called hash maps or dictionaries in other programming languages. Unordered maps can also be viewed and operated on as what is known as an associative array, where the index of the array can be any data type. In general, it's assumed that these data types have a hash function. If they don't, we can always implement a custom hash function for some of these data types. So here's an example. I'm creating an alias to an unordered map where the index is going to be a string and the value that is being stored is an integer. So notice that there are two generics when we define an unordered map. So we have two different template parameters. The first one being the key or the index into the unordered map, and the second one is the value being stored. So notice that in the next line, we are creating a object called wordNum which is essentially an unordered map based on the alias, and then by initializing it with three values. And here, the way it looks is the first one is the index or the key, and the second entry in each one is the value being stored there. So think of the word one as an index, and the value is -1. The word two is the index and the value associated with it is -2, and the word three is the third entry, and the value associated with it is -3. Since unordered map works as an associative array, you can simply access it as if it's an array. So word num within square bracket 2. Notice that here we are not using numbers for indexes. Instead, we are using strings because that is what we are defined as the index or the key into the unordered map. So here word number 2 refers to the value that is associated with index string 2, which in this example is -2. So here word number 2 is -2. Notice that we are accessing as if it's an array. So unordered maps are also called associative arrays because they associate a key to a value. Unordered maps or hash maps is a versatile and important data structure because access into it, the entries takes only a constant time in time complexity. Consequently, it is widely used for reducing time complexity of many algorithms. Keep in mind there was an urban legend, and this urban legend is very true. If you feel stuck in a job interview problem at times, most likely the answer to that problem was to use an unordered map. So keep this tip in mind when you're working on a lot of job interview type questions. If you feel stuck or if you feel like you're not able to get the most optimal solutions, think about unordered maps. It'll most likely work out for a lot of these problems. It is that important, and there are many memes on the internet about the use of unordered or hash maps. So keep this hash map or unordered map in mind and become conversant with it because it's going to be very helpful in job interviews. Let's look at an example of an unordered map. To use unordered map, you have to pound include the unordered map header. And then let's create an unordered map with string integers. Here I'm going to create a constant map which just has the name of the month and a number of the month associated with it. It's just initializing the unordered map. And let's iterate over each entry in the map and print each entry. Notice that when we iterate over this entries in the unordered map, notice the use of the auto keyword, and notice how we access and print pairs of entries in unordered map. Keep in mind with the unordered map, you're working with the key and the value. The key is stored in the first, so entry.first is the key and entry.second is the value. So this program basically iterates over each entry and prints the entries that we have added to the map. Note that the order in which entries are printed will be different than the order in which they were specified because the unordered map doesn't maintain order. So that's why it's called an unordered map. So there's no guarantee in the order, but the information will be stored there. Let's look at how to work with the unordered map as if it was an array. So here again, we have created a unordered map with three values, 1, 2, and 3. Now we can add an entry to it. So when you say word num within double quotes 4 equals 2, it adds a new entry to the unordered map, the key being 4 and the value being 2. Note that when you use the square bracket notation, a new entry is automatically added. So you cannot use square bracket with constant unordered maps because square bracket modifies unordered maps. If the unordered map is constant, you cannot use a square bracket. Instead, you have to use the at method for constant unordered maps. You can also update existing entries. If the entry already exists, the unordered map will update or modify the entry. And notice how we access these values using array notation, so it makes life somewhat easier. Let's look at another example of an unordered. Here we are specifically using a constant map. So we will not be able to use the square bracket here because square bracket modifies it. But if you want to find an entry in it, there's a find method. And notice how the find method is used. We say find some key, so here you're looking for 1, 2, or 3, find the key in the unordered map. If it is equal to the end of the unordered map, that means the key was not found. If it is not equal to the end of the unordered map, then the key is found. That's the logic there. And here it looks for the word and prints whether the word is found or word is valid or invalid. Again, keep in mind we cannot use a square bracket because square bracket will add an entry if it doesn't exist. We don't want to add an entry, we just want to check if an entry exists. So you will have to use the find method in this context. So keep that in mind. Let's look at some few examples to read and write maps just as a handy reference. Here we are going to create an alias called a type, and then we are going to create a string map. Notice the use of nested aliases as we go through. So here we create an unordered map that the key is a string and the value is also a string. Here's an example of a simple write method that iterates over each entry in the map and prints the first and second within double quotes. Here quoted is used so that if the first or second has multiple words, it'll be handled. Let's look at the opposite here. To read the map, again here, notice how two values are read from an abstract input stream. So from the previous presentations, you know, working with abstract input and output streams is a better way, so you can use different kinds of streams with these methods. Here we read pairs of values using quoted method, the converse of the printing. Notice how quoted was used to print. Quoted is also used to read. So these two are symmetric patterns to keep in mind. So as long as we're able to read a pair of values, we add the pair of values to the map that is supplied as a parameter to this method. Keep in mind, of course, the map either adds a new entry if it doesn't exist, or will update an existing key if the key already exists. All right, now that we looked at containers, just quickly review the rules of thumb for good C++. Again, so far we never used the new operator, and you should never be using the new operator in C++ in modern C++ anymore. For reading, prefer the greater than, less than, just like we did with unordered maps and such. Keep all of your comparisons simple. Keep in mind the parameter passing conventions. Prefer pass by value only for primitive data types. For objects, you should always prefer to use reference and preferably a constant reference. And now always prefer to use a std vector instead of a conventional array. So don't use conventional arrays in modern C++. Instead, prefer to use a std vector instead. All right, now we've got a lot of basic concepts done. We've got functions and methods covered in previous parts. We've also looked at input-output streams in one of the previous parts of this video. And this part, we looked at data types or containers, specifically looked at vector and unordered map. These two are very important data structures which are very often used in almost all programs will have some use of vector or unordered map as they become more sophisticated. And there are synonymous names for these data structures in other languages. So make sure you're able to draw a parallel between these names and some other data structures that you might be familiar in other programming languages. And the next series, we'll look at a brief introduction to object-oriented programming in C++. Thank you.